Hey everybody, today I'm going to be doing a little bit of group theory. So I've done some field theory on my channel before, but that's just some basic proofs, some short videos. Today I want to do a little bit of a group theory proof. I'm going to prove that phi, a homomorphism from G to H, maps the identity of G to the identity of H. So let me just draw a little pictorial representation. So basically, if we have a group G and we have a group H, and we have a homomorphism that maps from G to H, we'll call that phi. It will take the identity of G, which let's say the identity is here, so the identity of G, to the identity of H, and it will map it to that identity. So basically I'm proving that a homomorphism will map identities to identities. And remember that if we have the group, let me say G comma this operation, just an open circle, and we have H comma some closed circle, right? So remember that the special thing about homomorphisms is that phi of, I don't know, two elements, I'll say G1, G1 composed of G2, is equal to phi of G1 and then composed with phi of G2, where this is the operation from G and this is the operation from H. Okay, well let's actually prove this. This is really not a hard proof at all because we can utilize this little fact here, and we can say that, let me just do it down here. So we have phi, if we have phi of the identity composed with some element, so I'm going to say E sub G composed with some element G, and I'll explain that this is an element of big G. If we have phi of, and actually let me specify the actual group operation. So this is G comma open circle to H comma closed circle. There we go. That's more specific. So if we have phi of this is automatically going to be phi of E sub G composed with phi of G. Okay? Like that, based on this formula, right? So then I'll say this is for G and big G, right? Okay, well now, we know that phi of E sub G composes G. This is just phi of G, because the identity is defined to just kind of do nothing and leave it as G. That's what an identity does. And so then we know that this phi of G is equal to phi of E sub G composed with phi of G. And if you notice, we have this and this on both sides, so we can do the inverse. So let me just do, technically I'm doing like a right multiplication, so let me move this over here. So we have the phi of G, I'm going to move it over here, right? So then I'm going to right multiply on both sides, because we don't know if this is abelian or not. So we have phi of G inverse, let me put the composition there, and then I'm going to put the composition here. So it's the inverse of phi of G, right? So this is going to turn into E sub H, right? Because this is now the identity element of H, right? Because it's in the codomain. And this is going to be equal to, well, we have phi of E sub G, and then composed with E sub H, right? Because that's the same reason we did that. So this is composed with E sub H, and E sub H, we'll just leave it there. And again, E sub H, it's going to vanish because it doesn't do anything to phi of E sub G. So we have phi of E sub G by itself now. And yes, we have shown that phi maps E sub G to E sub H. And so we can just conclude that phi maps E sub G to E sub H. Because these are just equivalent statements pretty much. So yeah, that's the end of our proof. It's a very, very easy theorem to prove. Very just not hard at all. And yeah, it can be used in a few other things, so I might use this in another proof in the future. So I hope you guys enjoyed, and yeah, I'll try to do some more group theory if you guys want. So yeah, I will see you in the next video. Bye guys.